Okay, very good. So my talk is on analysis by synthesis, so I'm not sure how many people in the audience know what I mean by that. But for me, I'll start off by giving a brief history. The history, I must admit, is very biased. Somebody is pointing out a problem with the projection. Why is that happening? We don't know. What's going on here? Okay. Okay. Finally, thanks. Okay, so I'll start with a very brief history of analysis by synthesis. It's going to be a bit biased to perhaps some of the early work that was originally done at Brown, Harvard University, then at UCLA. There is a neural network history, but I started trying to prepare some, but there's no time, there's no space for it. I'll give some computer vision examples. I have one slide on neural network generative models because there was no space for more. And then I'll talk about approximate analysis by synthesis. And the talk is geared towards the question about how can visual recognition, and I'd say, frankly, not just visual recognition, any visual task, recognition, segmentation, part detection, anything, benefit from generative image models. So analysis by synthesis, this is a brief history. Now, nobody's ever written a history of AI, but my view on it is that we keep going round and round in circles. Ideas become popular, then they become unpopular, then we come back to the same ideas some years later, which is discouraging in some ways. Things fall out of fashion. Neural networks were in fashion, they were out of fashion, they were in fashion again, they were out of fashion, now they're very much in fashion. Is that going to continue? Probably some aspects of them will continue, but I'm not convinced that, I don't think current deep nets is the final solution to vision, and that's based on my experience of continually going round in circles. And there's a quote from a great philosopher saying people who do not study history are condemned to repeat it. What happens there is that I think good ideas get created, then they get forgotten, then they get rediscovered, and people realize they're very good in practice. There are many examples of neural networks in this third generation of neural networks, which were around in the second generation with hardly any citations at all, and then people finally realized later that they were very good. The positive aspect of this is even though AI progress seems to go round and round in circles, there's an important dimension, which is the performance dimension, which keeps increasing. So as we go round in circles, we're really going round in a helix. So our performance gets higher and higher each time we go round in the circle. And that's encouraging. That's because whenever we come back to a problem that people have tried before and it's only partially worked, we now have more technology, more ideas, and I would say infinitely more people working on the problem. And so I hope this will be true for analysis by synthesis. So what is it? The idea is that there is a type of duality between how images are created, how they're synthesized, and how they should be analyzed. This was first formulated by Alf Grenander at Brown University in the 1960s. I think he even wrote about it in the 1950s. Grenander developed this idea that influenced various people like Stuart Schumann and so on. It led into certain Bayesian ways of working on vision. It influenced the Harvard Vision Group, which I was a member of, before Harvard decided that vision was not a promising area of doing research, and neural networks were even less promising area of doing research. So the core idea is that you would if you have models for synthesizing images, and in Bayesian terms, you'd have a probability model for generating an image conditioned on W, where W is the world state variable, that you would do analysis by inverting the process using Bayes' theorem. You would compute the probability of the world given the image by taking into account the probability of the image being generated by the world, P of I given W, times P of W, the prior. And on the right-hand side is a very nice illustration of this by Pavan Singer from MIT. You have the image of a cube, and everybody looks at that image and says it's a cube. But of course it isn't. It's an image of a series of lines on a flat plane, but somehow everyone who looks at that thinks it's a 3D model of a cube. Why? Pavan's explanation is to say that you think of every possible way, every possible object in the world which could generate that image. And that rules out a lot of world objects like spheres and cylinders, which could never have generated that image. And so you're left with a set of simple models on the bottom on the left. Of those models, there are many of them still, but you choose a cube for various reasons. Maybe a cube is more likely to have cubes in the world than anything else. Maybe to see it as a cube, consistent with a cube, depends on the viewpoint, which is an idea from Bill Freeman. So this is getting a little bit overly complicated, but bottom line, analyzing images should be the inverse of generating images. Now, again, just to contrast that with a lot of current deep network work, at least CNNs, transformers, etc., they are trying to learn P of W given I directly. They're not trying to learn P of I given W or P of W. This has advantages. It's a lot easier. It's also got some major disadvantages, I would say. Do humans use analysis by synthesis? This is, this is the brain. The brain is complicated. Nobody really knows, but there's quite a lot of evidence that it happens. And my colleague, friend Dan Kirsten, argues that human visual system performs approximate and is needed analysis by synthesis. Approximate meaning is that you don't do this perfectly and reconstruct a 3D world. And as needed is that most of the time you don't bother because there's no reason for you to do it, and it may be difficult to do. Again, I should have said analysis by synthesis is like inverse computer graphics, but it dates before that. At the time that Alf Grenander formulated it, computer graphics didn't exist as a subject. And there's a time that it got picked up by parts of the computer vision community. The state of computer graphics was so weak that, when they had conspiracy theories of saying that the Apollo landing was faked by computer graphics, anyone who knew about computer graphics knew it was a lot easier to build rockets, put humans in them and fly them to the moon than it was to have simulated it realistically using computer graphics. This has changed now. Computer graphics is now an advanced area, and generative neural network models have played a role in helping it to become so. So this is where analysis by synthesis links into computer graphics, etc. Neuroscience. 20 or so, 30 years ago, David Mumford. I don't know how many people here know of him, but he is one of the two very clever people I have interacted with in my life. The other one was Stephen Hawking. David was a pure mathematician, a very good pure mathematician who got interested in vision and thought very deeply about it. So he really embraced this approach. He also showed that it could be related to the structure of the brain. This is concepture, not complete evidence, that the feed forward and feed backward paths in the brain relate to analysis by synthesis. Now, this doesn't mean necessarily anything, and the fact that David Mumford is a really highly intelligent man. Doesn't mean that he was right about this, but for me, at least, it makes me think about it. A second point, which relates to ideas perhaps coming up in machine learning, is that analysis by synthesis requires generative models, and these are causal. Causal in the sense that they generate images from the 3D world, from the geometry, the texture of the material, and the light. This enables analysis by synthesis to generalize data that differs from data the algorithms are trained on. There is papers about this by Joshua Mbengio, Bernard Sholkoff, etc. in machine learning, unrelated to vision, but the same point applies. If you want algorithms that generalize outside the training data, a very good way of doing it is to build causal models that have causal understanding of how the data is generated, not just, which requires generative models, not just classification. And so there's a physics analogy. Since I started out in physics, Newton's laws of gravity predict the motion of the planets. They have a model which has one parameter, the gravitational constant, and it generalizes, it works on the planets, it works on objects in the laboratory, it works on apples falling from trees. It doesn't require a huge amount of data. Before that, there was the Ptolemaic theory of the universe that was tinkered with, fit to the data, gave wonderful fits to the motion of the planets, much better than the fits that Newton's theory had, at least for 50 or 100 years after Newton. So very good for predicting the motion of the planets, but completely unable to generalize to anything else. So I think we need more Newton-like theories which have causal understanding, and I would argue that analysis by synthesis using generative models is an example of that. So analysis by synthesis, this is from a review paper I had about 20, not quite 20 years ago yet. But it's saying analysis by synthesis really depends on the complexity of the real world. If you have a simple world which consists of letters, then having a generative model for that world is very easy. The synthesis is easy. However, the analysis, which means you start with those images and work out what generated them, is easy also. However, as you move to a more complex world in B, you need the generative models don't become much more complicated, but the inverse process of taking the images and working out what's generated them becomes a bit harder. If you move to world C, you have a world where generative processes are again reasonably simple, but you're generating complex images, and so inverting them to find the what caused them becomes incredibly difficult. These things are captures. In fact, I think we might have written the paper before captures were invented. So, hey, maybe we missed a lot of money by not realizing that this was this had practical implications. But our goals were conceptual. The world is complicated. That requires complicated generative models, but inverting those models becomes, in a way, even more complicated because you have to search over all possible ways the images could have been generated. So here are the challenges. It's conceptually very attractive, and so I've thought for at least 30 years that the final solutions that we'd have with computer vision should be based on analysis by synthesis, but it has been very difficult. And what are the main reasons? First reason is that synthesis is hard. It requires generative models of images or image features conditioned on the world states. It seems now that we're moving to a situation where those types of models exist, although I'll have some caveats about a lot of the neural network generative models, which I'll mention the slide later. The second point is analysis is hard. Inverting generative models of images is not easy. The worst case is you search over all possible ways that an image could have been generated, which is impractical. You can, of course, simply train a regression model to do it like a deep net. I have various reasons where I'm, where I don't favor that approach for doing inverse generation of images. A third point is also that evaluation is hard. Current annotated benchmarks are not designed for evaluating analysis by synthesis. The research field, this is changing a bit now, but we're working in a train test paradigm where you have data, train on the data, you test on similar data, and you try and squeeze a few AP or a few fractions of AP out of your performance, and then you publish a paper. This is, in my view, not a great way to do vision, but a lot of it is done that way. If we want to show that other algorithms are important or other approaches are important, there need to be benchmarks on them, and the benchmarks need to be challenging, and the community needs to accept them. So here are a few examples going back to 20 years ago, and I'm slightly encouraged that just before the talk, somebody told me how he liked my 20-year-old papers. I hope he doesn't mean that he doesn't like my recent papers, but to be frank, I prefer these old papers myself also. And so here are 3 examples of analysis by synthesis, which illustrate certain properties which can happen in current AI algorithms, but perhaps don't happen very often, and they may suggest approaches to them that can be useful. One is on Bayesian edge detection, another one is on image parsing, done with Zhou Chu and Songchong Zhu, who has been a big advocate for analysis by synthesis, and other work by my student Leo Zhu. So here, very quickly, just to hopefully give the context, edge detection and domain transfer. This was done by my student, Scott Kanishi. This was just at the beginning of the Bing data sets. BSD, standard data set for edge detection, did not exist at that time. It was actually motivated by Kanishi's work. Jitendra Malik was on his committee and thought, okay, let's have a better data set. But the core idea here is if you perform this in a generative approach where you're generating feature vectors, then if you have 2 data sets which are really quite different in terms of in terms of the complexity of the images, it's quite possible using Bayesian methods to get domain transfer working between these 2 data sets. One data set consisted of images inside houses in Florida. There was almost no texture in the background. What texture there was had been removed. The other consisted of images of the English countryside, which had a lot of complicated texture and stuff. In the work that Kanishi did, you could train on the South Florida images, and you could get them to work on the English countryside images without any annotations. This was domain transfer. It fell out of fashion. It's now becoming more fashionable thing. And so my point here is that just the Bayesian approach gives a very natural way that enabled us to tackle domain transfer 20 years ago. It may not be the best way to do it, but it was a particular way that comes from thinking in a Bayesian analysis by synthesis approach. Another example was work with Zhou Chu and Songchong Zhu. This was image parsing, and there are many things could be said about that, but the point I want to make here is that you could do analysis by synthesis very quickly. It used a method where you took feed-forward methods to make proposals for generative models. The generative models then could be validated by the work on the images. This was actually, it was complicated but successful. It was state-of-the-art on the edge detection data set, one of the papers. The second one won a Mar Prize for whatever that means. It's I guess the point here is that doing generative models on realistic images is possible, and Songchong Zhu would have series of work on that. Another one was related to seeing if you have generative models, there are fairly natural ways to do unsupervised learning of object models and object grammars. And you could have algorithms trained on Caltech 101. This was Fei-Fei Li's first data set that became popular. Obviously, it got moved and forgotten about in ImageNet, and there were many issues with, with the data set. Easy to score on it, easy to get almost perfect performance on it in various ways. But you could get performance without any supervision on that data set by using this type of approach. Generative models, objects, object classes, building grammars for these by my student Long Liu Zhu, Yonghao Cheng, and myself. The series of papers on this, I would say Liu Zhu, by the way, for people who care about high-tech companies, is a founder of E2 in China together with Yonghao. So they're probably either billionaires or will be billionaires. They have a lot of ability. And however, the thing that they did, which I like most, is this type of work here. And the second type of work extended, which included other people like Antonio Tarabla and Bill Freeman. So at this stage, part two summary, how am I doing for time? 5 minutes, okay. The rest of the talk's going to be impressed, is that generative models analysis by synthesis are very attractive conceptually. Advantages include learning without supervision, domain transfer, performing multiple vision tasks in a consistent manner. They require data sets, challenges that differ from those which are standard in computer vision. And I predict they will come back in fashion, at least I hope they will, in the same way that deep nets were out of fashion 10 or 15 years ago, and people couldn't get them published. Now, part two is involved with Adam, but it seems there's no, well, actually, part three is neural network generative models. Much to say, even less time to say than I intended. My concern of them from the analysis by synthesis approach is that they have models of images conditioned not on world variables, but on various latent variables. These latent variables may sometimes be interpretable, but they may not. And a recent example that illustrates that is the paper I'm mentioning here by Qihao Liu. Adam's also a co-author, where you show you can attack these models so that you can get them to generate images which have got nothing to do with what you want to generate with them, just by playing around with their latent variables, etc. So I think these models are wonderful. There's a huge opportunity with them, but for me, I'd like them even more if they could generate images conditioned on the world state rather than conditioned on latent variables and text prompts. But still huge, really important, really interesting work there. But I'm giving you my bias. Okay, so next talk will be really short, and this is approximate analysis by synthesis done with Adam, Antieng, and other people in my group. The idea is that you have a generative model that actually isn't realistic as generating the images. It's able to generate certain features. It makes all sorts of assumptions for generative models, which are bad if you want them to generate images, like it factorized. It makes lots of independence assumptions. Okay, so it's not a great generative model, but it's got one nice property that you can analyze it. You can learn these models, you can do inference on them fairly quickly, and then you can get some of the nice properties of them. This dates to another strand of work for analysis by synthesis in computer vision, which comes out from Thomas Vetter and his group in Germany, where you do render and compare. Essentially, these models will do render and compare on image features. It can do nice things like detecting and getting the orientation of cars, even when they're included by gigantic or by anything else. It can do 3D pose estimation under really heavily occluded situations because, again, the properties of generative models. It can do object classification. I'm not sure I believe this example. My student told me it was correct, that you can even classify a car when it's occluded by a gigantic cat. Now, probably people here do not care about gigantic cats occluding objects. We have done other studies where the performance also works if the occlusion is real or natural. However, it's harder getting that type of annotations. And so using gigantic cats or other objects is a nice surrogate for this. Also, these will generalize. I mentioned this is a property of analysis by synthesis. They will start being able to generalize to other conditions, different weather conditions, different pose conditions, and things like that. Here are some tables which I ignore. We need them to get papers published. I usually don't bother to look at them afterwards, but they are saying that the models do well on current benchmarks and are very much more robust to out of distribution situations. So I don't mean approximate by instance is sort of like an initial attempt. It's work in progress. It's working on limited numbers of objects. There are many limitations to it at the moment, which hopefully will be solved over the summer or by next year. But it does give some proof of concept that you can get certain types of analysis by synthesis methods working in a way that they can compete with standard deep networks on regular tests, do as well, and yet be far more robust if you test them out of distribution. So here's a conclusion. Do I have a minute or less than a minute? 1 minute. So analysis by synthesis is an old idea. It's conceptually very attractive way to do vision. I think it's perhaps, from my view, it's sort of the deepest way to do vision, united now computer graphics, computer vision, and a whole bunch of neural network type things. And it means you can perhaps do every visual task with it in a consistent manner rather than just training different heads on a foundational model to do different tasks. Okay. And it may be how the human vision, how brain does it. It shows promising results. The approximate method shows some nice promising results showing that certain of the advantages of analysis by synthesis can be developed using current data and using current benchmarks. But concluding, it's very difficult. It's not in fashion. We've got a very big hall here. We've got a reasonable audience, and perhaps we've got other people online, but we haven't got 1,000 or 2,000 people. And so I guess the goal for next year or the year after for people like myself who believe in analysis by synthesis is to convince enough people so that we will fill a hall this size by people who are interested in it. So we need the tools. We've got a lot of the tools. We need the motivation. Some of us have. And again, this is getting back to the helix of vision. Some of these ideas are old. Performance went up to a certain level, plateaued, stopped. Coming back with these new techniques means I think these methods are going to work a lot better. And this is going to happen very soon. Thank you.
Thanks, Alan, for this fantastic talk. We have time for 1 or 2 questions. And we have Kun Hao over here with a microphone. So, yeah, Kun Hao, you decide to.
Thank you for the great talk. So I have one question. Is that like bistable images?
Which image? Sorry, which images?
Bistable image. For example, the Jastro duck. Like it looks like a duck and also looks like a rabbit, but you can only see one thing at a time. You cannot see them both, right? And I wonder, I think it's one example of the analysis by synthesis. I'm not sure what's your opinion about it and how analysis by synthesis or current deep network can solve this like bistable image problems.
Well, from the analysis by synthesis perspective, I guess, you get both solutions out. You'd synthesize both, you'd find both of them were consistent. and the theory would deal with that well. To account for why humans see one and humans see the other, that seems to be partially memory effects or priming effects, etc. But from the from the Bayesian approach, I see Bayesian analysis by synthesis approach, I see no difficulty with it. But actually, for that, I'm not sure I see a difficulty with feed-forward deep networks either. You could enable them to output several possible solutions with confidence, and I think you'd solve that also.
Yeah, I guess. Thank you.
Okay.
One more question.
Okay.
Yeah, so I always confront this because analysis by synthesis is kind of uses optimization techniques to solve, whereas deep CNNs and deep networks are feed forward. So how do you, how can you combine these two paradigms?
Well, I guess, oh gosh, one of my least cited papers, which happened published in an obscure place just at the end of the second phase of neural network, suggested that you can, any optimization problem in vision, you can always solve by training a network on it. And we had examples. So you can always do it by regression. I don't actually advocate that. I think the one strategy was in these papers with Zhou Chu and Songcheng Zhu that you find good proposal probabilities that may not be correct, but are good enough to activate a limited class of top-down models. And yes, I'll say more about that in a few months, possibly, or maybe after lunch with Adam. There are ways of doing that. You have to, inverting the really complicated model, it's not possible for something like this. You need to break it down in components, and you need to find approximations to it that you can solve easily, factorizing things, bag of words sort of models, etc. They will make mistakes, but as long as they're aware they make mistakes sometimes, as long as they're, even their second solution, their third solution, their fourth solution is good enough, then the generative models can check out and find which ones are correct. If that's, yeah. Thanks. Okay, thanks.